provided the omega t's evolve by minus the 1,1 part of the Bismuth-Ricci form, and the beta t's evolve by the 2,0 part. Mario talked a little bit about exactly what the Bismuth connection is, so I don't really want to spend too much time on it, but it's the unique Hermitian connection with totally skew symmetric torsion on M. Yeah, I guess I should mention that omega naught should be pluriclosed. Yeah. Oh, how do I? Is this not going to want to cooperate? Sorry, I'm having some minor technical issues here. There we go. Okay. Yeah, so omega naught should be pluriclosed. And Streets and Tien have checked before that this flow preserves the pluriclosed condition. So the Bismuth connection makes sense. We're all square here. All right. Yeah. Holomorphic current algebroids, it turns out, are going to be a really useful setting for examining pluriclosed flow. But we're going to need to do a little bit of work first. So the first thing we're going to want to do is we're going to build out a Schwartz lemma that'll be particularly useful in the setting of pluriclosed manifolds with holomorphic current algebroids. And it'll help us with our a priori estimates along the flow. The next thing I'd like to do is talk about kind of the changes, the formal changes that happen to pluriclosed flow when you view it as a flow of Hermitian metrics, generalized Hermitian metrics on a holomorphic current algebroid. So this is really the place we're going to be talking about pluriclosed flow on holomorphic current algebroids. After that, I'll be talking a little bit about convergence on Bismuth flat backgrounds, convergence on Bismuth flat manifolds, four is going to be a really quick section, but this ends up giving us a nice result showing the contractibility of the space of generalized Kähler structures on Bismuth flat manifolds. So this is going to be a quick sort of GK geometry, GK structures on Bismuth flat manifolds. And then the fifth thing I'm going to talk about is long time existence. Long time existence on complex surfaces having non-negative Kodaira dimension. So let's go ahead and start at Schwartz lemma. So the first thing I want to mention just really quickly is if we have omega over, or sorry, capital W, a holomorphic vector bundle over a complex manifold. Then we can define the Chern Laplacian on smooth functions over M once we have a metric on M. Okay, so if G is a Hermitian metric, on M, then we can define the Chern Laplacian just to be the following. The omega trace of I dd bar F for any smooth function over M. This is just a definition we make to make some of the following make a little bit more sense. All right, so let me just kind of start with a statement of the classical Schwartz lemma. On holomorphic vector bundles. All right, so the place to start is with sigma, a section of our holomorphic vector bundle W that I defined earlier. Then for any Hermitian metric, H on W, right? Turning it from just a holomorphic vector bundle to a holomorphic Hermitian vector bundle. We have that the Laplacian, right, the Chern Laplacian of the norm of sigma squared in the H norm, right? This is now a smooth function on M, is going to be given by a nice positive term minus a term involving our second Ricci curvature. Okay. And just as a reminder, I think it's worth mentioning that SGH is the so like the omega G trace of the H Chern curvature, right? And this is a section of the endomorphism bundle. All right, so just as a reminder of what that is, because we're going to come back to that a little bit later. It's going to keep popping its head up. So this notation will be really useful. Okay, so this is the classical Schwartz lemma, and it shows up all over the place. It ends up being really useful for getting like trace G tilde estimates all over the place. But in particular for us, we'll be using it in a couple different settings. Okay. So the setting that we'll primarily be looking at is E, F, phi. So E is a holomorphic vector bundle over M. F is a holomorphic vector bundle over N. And phi is a morphism of holomorphic vector bundles covering little phi. Okay, so this diagram commutes. and M and N are complex manifolds. Now, something to think about, right, is that we can identify phi. We can identify phi with a section of E star tensor the pullback bundle of F, right? So a section over M of this bundle. So this is like a slight abusive notation, but it's one that it makes a lot of sense. And we actually find that we can apply the standard Schwartz lemma in this setting once we put metrics on everything. All right, so a quick result, a lemma from our paper, Garcia Fernandez, J, and Streets, which I guess is probably more widely known. With this setup, right, with this setup, if we put Hermitian metrics on these vector bundles, for any G Hermitian metric on E and G tilde, a Hermitian metric on F, and yeah, okay. If little g is a Hermitian metric on capital M, then we get the following Schwartz lemma. All right, so the Chern Laplacian associated to little g of the norm of phi squared taken with respect to what I'm going to call script g real quick. And I'll elaborate on what script g is in just a second, is going to be this nice positive term. The Chern connection associated to script g of phi squared, where the norm is taken in little g, and script g, plus, it's kind of funny term, SG capital G minus phi star SG G tilde composed with phi taken in the script G norm. And script G is just the metric that G and G tilde induce on this bundle right up here, right? E star tensor the pullback of F, right? So script G is just G inverse tensor the pullback of G tilde. All right, so there's nothing too surprising in here. The proof is really just to apply the usual Schwartz lemma on our commuting diagram from before, right? All of that induces this metric G tilde on E star tensor the pullback of F, and then everything just kind of pops through. Okay, I guess there is one small thing to mention. So just a quick remark is that this quantity, acting on E, some section of E, right? E is section of E. It's the difference of the Chern connections on E and F, right? So this ends up being pullback of the G tilde Chern connection acting on phi of E minus phi of the Chern connection associated to G of E. All right. So a lot of times in the paper, we end up calling this, I believe, AG G tilde acting on like E, because it's a nice tensor and it's a lot like a second fundamental form. And with this formula, right, you can actually see that SG script G is, I believe, the negative. Yeah, so it should be this guy. G tilde composed with phi minus phi composed with SG. Right, as like an equation of endomorphisms of E star tensor to pullback F. Okay, with this stuff in hand, it becomes pretty clear that this is just a special case of the classical Schwartz lemma. All right. So this is a useful lemma for us. But we actually want to specify it down a little bit. So I'm going to make a quick definition. We have this quantity upsilon, G tilde. I believe upsilon is pretty standard notation for this. And it's just the difference of Chern connections. G to G tilde C in T1 0 star tensor endomorphisms of E. And I guess I should just mention that G and G tilde here. G and G tilde are Hermitian metrics on E. Okay. So you can see kind of the relationship between upsilon and this A quantity that I've mentioned in the setting where phi is the identity. And it turns out that the setting where phi is the identity is the one we're going to be most concerned with. So another quick lemma from the paper is if E over M is a Hermitian vector bundle. Sorry, holomorphic vector bundle. It's a holomorphic vector bundle over a complex manifold M over complex manifold and G and G tilde are both Hermitian metrics on E. Then we have a Schwartz lemma that looks more familiar, right? It looks a lot like something we would need for an a priori estimate. G tilde is equal to our nice positive term, or I'm sorry, our nice, positive term, upsilon g tilde squared, and then in the correct metrics, like g inverse g tilde plus the trace, the g trace of SGG minus SG G tilde dot G tilde. Okay, so the trace is over the dots. Where does this come from? Well, I mean, it's really just a specialization of our prior lemma, right? So it's just this Schwartz lemma for holomorphic Hermitian vector bundles with m equals n, f equals e, and phi equals the identity map. So take m to be n, f to be e, and phi to be the identity in our last lemma. Phi to be the identity in the Schwartz lemma for holomorphic Hermitian vector bundles. All right. At this point, the proof is pretty short. It's really just like a corollary of our prior result. Something to notice is that this even applies in the setting where G and G tilde are how did I want to say that? Are generalized Hermitian metrics, right? Yeah. So I mean, mark generalized Hermitian metrics. Mario mentioned that these can be thought of as like particular subbundles with extra data. To these, I believe he also mentioned you can associate like Hermitian metrics, and they really just end up being conjugates. So like I believe the general setting, like G beta, is E beta G 0, 0, G inverse e to the minus beta R. Yeah. These guys are special cases of Hermitian metrics, right? These are Hermitian metrics. Hermitian metrics on T10 plus T star 10, right? On our holomorphic Courant algebride. So like specifically, as long as beta satisfies some certain integrability conditions, we can put this guy, so like in particular, as long as like del bar beta is del omega naught minus del omega G, then this, right, G is a Hermitian metric. On our holomorphic Courant algebride, like this background one. All right, this omega naught guy. And because it's these generalized Hermitian metrics are Hermitian metrics, we can apply this lemma right on the nose. But we have kind of something else that's useful And that's really just that these traces are interchangeable. And this will end up being useful for us. Okay. So that's kind of everything on the Schwartz lemma that we needed to prove to get some a priori estimates in a minute.
Can I ask a question for what you wrote?
Go ahead.
Could you just scroll up? What is the omega 0 there?
I was
omega 0 and omega g.
I was kind of jumping the gun a little bit, but omega 0 is just some pluriclosed metric on the manifold that's like Dolbeau cohomologous to omega g, and omega g is just g j dot. I'm like jumping the gun a little bit. I'm just kind of describing why this Schwartz lemma is useful in our setting at all.
And what is G tilde? It's just another one of those?
G tilde. Yeah. So like G and G tilde, generalized Hermitian metrics, they, I think you might need one to be like diagonal without the B field transformations. Yeah. But this happens. So like G would be G beta, and G tilde could be something like some background pluriclosed metric with like no B field transformation. Then you can trace it either way.
And can I think maybe this is due to just my confusion of forgetting how the definitions work, but for a generalized metric, isn't it right? Isn't it the case that it's not positive definite? Like there's a subspace where it's positive definite and a subspace where it's negative definite. Do you have you don't have the same issue with the generalized Hermitian metrics?
That's a good question. I think it's that the neutral inner product is indefinite, but the like generalized metrics, I thought you needed to pick an endomorphism so that the whole thing became positive definite.
Yeah, I guess here we're like already applying the neutral inner product, sort of. So we're not quite using the term, I guess, the way it's used in other places.
Okay, yeah, I understand now what my confusion was. Yeah.
The holomorphic Courant algebroid is a reduction from an exact Courant algebroid. So you can identify it with B minus. So what we call generalized Hermitian metric is really the C-linear extension of a metric which is positive definite or negative definite on B minus. So it's definite. There is no problem with it.
Okay, thanks.
Yeah, that clears it up for me too. Yes, thanks, Mario. Yeah, I have a bad habit of, I tend to just think about these guys in coordinates. But yeah, so like if I'm stumbling over something there, please feel free to hop in. All right. So a proposition that we prove in this paper, well, I mean, I guess Yeah, we prove it in this paper. So Garcia Fernandez, Jordan, and Streets. Is that pluriclosed flow is actually like equivalent to a sort of Hermitian-Yang-Mills kind of flow of generalized Hermitian metrics, which is kind of why I wanted to bring that up. So I'm going to take M2N, GT, beta T, J to be a solution to pluriclosed flow. And then we can define GTs using this formula I mentioned before. So G, GT, beta T. Right, so just using this formula here. Okay, we can cobble together some associated generalized Hermitian metrics. GT are generalized Hermitian metrics which satisfy a certain PDE. Hermitian metrics on a holomorphic Courant algebroid, right? All on the same omega naught holomorphic Courant algebroid, satisfying G inverse dg dt. So let me keep my t's on here for now. Minus s gt gt. And this perspective has actually proven really useful. Me and Jeff wrote a paper where we were able to get some a priori estimates. I think I make reference to it later. Using the fact that, right, on the holomorphic Courant algebroid, these generalized metrics flow essentially by like a Hermitian-Yang-Mills type flow. And these two things are equivalent. If you have this kind of flow for generalized Hermitian metrics, then the G and the beta have to solve pluriclosed flow as well. Really, like the key to this lies in Bismuth's identity. So just kind of a note. So just a quick sketch of the proof. I'm not really going to get too into it because it is just sort of a calculation. But the long and short of it is that the like Bismuth connection, the Bismuth curvature of G is in a certain sense, right? It's the same thing as the Chern curvature of these like capital G's. Except you interchange some indices. So when you trace this stuff, right? So when you take the appropriate traces, right? Taking the appropriate traces. You end up getting that like SGG is completely determined by rho Bismuth of G, right? I guess this is true without even the flow being present. So I don't really need that. Okay. And if you compute through everything, right? If you differentiate this G, written out by the formula we had before, you'll get exactly negative SGG, where this comes from Bismuth's identity. Right, this is one of the reasons we were so interested in proving that, because it gives us some really handy slope stability tools, like Mario presented last week. And it's also the big reason that we get this really nice flow equation when we move from the manifold and lift up to the holomorphic Courant algebra. Okay. Any questions so far? Yeah, I don't want to be too hand-wavy, but I also don't want to get too bogged down in the details either. With this flow equation, we can go ahead and derive some a priori estimates, or we can derive some evolutions for quantities that will eventually turn into a priori estimates. So this is Garcia Fernandez, Jordan, and Streets. If we have a solution to query closed flow, with associated generalized Hermitian metrics, GT, on the holomorphic Courant algebroid, right? So I mean, I guess just as like a little note, just as like a little note. This just means like del bar beta t is del omega naught del omega t. Right. Then if we're given another Hermitian metric, given G tilde Hermitian, on Q I del omega naught, when viewed as just like a holomorphic vector bundle, then we can find that the traces, the trace of G tilde with respect to G has this kind of heat equation. So nice positive term, G inverse G tilde, plus a trace S G background term, G tilde dot should be the G trace, the G tilde inner product. All right, now this is a useful flow equation. Yeah, this is a useful evolution equation in the setting of Bismuth flat, right? So like, hopefully this is kind of hinting at why Bismuth flat is going to be so useful, because this last term here, right? This last term, this vanishes if G tilde is Bismuth flat, or sorry, if G tilde is Chern flat, G tilde is Chern flat. But because of this correspondence between like Bismuth on the base and Chern on the holomorphic Courant algebroid, G tilde will be Chern flat when you've got like a little G tilde that's Bismuth flat. So these terms are going to drop out in like main case of interest. We've also got, so in my notes, I wrote these as like two separate propositions, but they're both flow evolution equations, so I might as well just put them together. dt minus delta of epsilon g tilde squared g inverse g tilde is going to be equal to, some nice signed terms, this is the Chern torsion contracted with epsilon form squared plus Chern torsion epsilon Chern curvature of g tilde epsilon bar Chern curvature of g tilde plus an epsilon contracted with the g tilde Chern covariant derivative of the g tilde curvature. So again, right, these are all background curvature terms. Right? So once again, these are all going to be really useful in the Bismuth flat setting, because this first term, it's non-positive, and these two first terms, they're non-positive. So we'll be able to use maximum principal arguments really easily, which is always handy. Yes, and then just as a reminder, epsilon is the difference between the Chern connections associated to G and G.
What does the circling of the three terms refer to?
Oh, yeah, so these, they all depend on the background curvature. These are all gonna vanish again if G tilde is Chern flat. Yeah, so I'm just highlighting that these are terms that are a little tricky to deal with, but in the setting that we're interested in this paper, they're not going to cause us a problem. Yes. Yeah. And then as for proof of these, again, I'll just kind of give a quick, so like just a sketch of the proof. For this trace one, it's really just the Cauchy-Schwarz inequality, right? So you can notice, so like ddt of trace g tilde is going to be the trace of G inverse SG G tilde, right? Where everything is an endomorphism. Or I'm sorry, the G's are symmetric two tensors, right? So like this is two down indices, this is an up and a down, and then this is two up indices. So this composition ends up being an endomorphism, so we can still take a natural trace. But you can rewrite this as the G trace of the like G tilde flat of this SGG. Right, these quantities are the same. And then you just apply the Schwarz lemma. right? The Schwartz lemma says that the Laplacian trace G tilde minus our nice positive epsilon squared term plus trace G of the background second term Ricci curvature minus this guy is equal to 0. So you can swap this stuff in for that. And that's exactly the evolution equation that we asserted. The other one is a little more complicated. It would kind of take some time to go through. But if you're interested, the other one can be found in work of Jeffenlein from, I want to say 2020. I think it got published in 2020. And in there, we do it in the setting where there is no omega 0, right? So we do this for d bar beta equal to d omega, like the evolving one. Right, like there is no omega 0, but the computation is purely formal. It proceeds the same way, but the computation is purely formal. Once you've got the evolution equation, this guy, right? Once you have this in hand, the computation goes through exactly the same way. So we have these evolution equations that are really handy for us. You can sort of imagine, well, okay, it's a little unclear about why they're handy for us, though. Because we're trying to get a priori estimates on little g and beta, right? These are our actual flowing quantities, little g and beta. So these two guys, right, this trace and this epsilon, these are things that you commonly estimate when you're looking for a priori estimates to flows. But like, why are we estimating the big G's instead of little g? Well, it turns out that, you know, you can go either way. So let me just, existence and convergence on Bismarck flat. Existence and convergence on Bismarck flat backgrounds. Kind of a small algebraic lemma that we proved in Garcia Fernandez, Jordan, and Streets is just that controlling the big G's implies control on the little g beta and the epsilon of the little g's. So if you've got g, which comes from right, a downstairs metric, so like g and beta, and g tilde, right, coming from downstairs data the same way. These are on the same holomorphic current algebroid. Then you can get that if there's a uniform lambda positive so that the metrics stay uniformly equivalent, And the upsilons are under control, then you get that there's an A, depending on lambda, so that the little metrics are uniformly equivalent. The beta is under control in the G norm, and the upsilon of the little g's, G tilde norm, is also under control. All right, I won't give a proof of this just because, again, it is a little bit of a computation, but the trick to it, right? So just a quick sketch. We give a coordinate formula. So we give gamma the connection coefficients of, sorry, let me say the Chern connection coefficients. The Chern connection coefficients of G, a generalized Hermitian metric, on Q in terms of, G and beta in the paper. In this paper, we compute like all the Christoffel symbols. And just by arguing on these coordinate identities, you can get kind of everything else. Once you know how to write gamma in coordinates, you know how to write upsilon in coordinates, and we already know how to write the G's in coordinates. So with all of that in hand, you just argue about specific components. The specific components are bounded, and those imply bounds on everything else. Okay. So like in particular, right? I guess just not to rush it too fast. If you think about G, right, the bottom right corner is little g inverse. So if you feed it two covectors, you can get all the components of little g inverse, and you know that it has to satisfy bounds like this. So you can get bounds on little g inverse, which imply bounds on G. Okay, so this is why I've been kind of talking about evolution equations for these generalized Hermitian metrics instead of our pluriclosed metric on a base manifold. Okay. So with all of that on hand, we can get to our first main theorem. And really, it should be all downhill from here. So I think Bestie should be able to get some sleep, hopefully, if he hasn't already. So M2N omega Fj is a Bismuth flat complex manifold. Then given omega naught, our initial metric, right? Given omega naught, an initial pluriclosed metric, pluriclosed, on the same holomorphic Courant algebroid, kind of a more standard, not a more standard, a more cohomological way of saying that. So given omega naught in the same holomorphic Courant algebroid, we can just say it this way. They define the same 2-1 Dolbeault class. The solution exists for all time. the solution to pluriclosed flow with initial data omega naught exists for all forward times and converges to we'll call it omega infinity, which is also Bismuth flat. It's not, we haven't been able to show yet that it's necessary for omega infinity to be omega f. I think we can show that in some limited cases like the Hopf manifold. So like when you have some explicit descriptions for the size of like H21, then you can sort of limit your options. But in general, we just know convergence to another Bismuth flat manifold. All right. So I'm going to oh, go ahead.
Question.
Yeah.
It's another really basic question, but what is the difference between Bismuth flat and Bismuth Hermitian Einstein?
So Bismuth flat is the full Bismuth curvature tensor vanishes. Bismuth Hermitian Einstein is that the first Bismuth Ricci tensor vanishes. So it's like the trace. Omega B vanishes is Bismuth flat. Rho B vanishes is Bismuth Hermitian Einstein.
And Bismuth flat implies Bismuth Hermitian Einstein.
Yeah. Oh, yes. So I'll just be denoting our background holomorphic Courant algebroid as QF, just to keep things from getting too sloppy. We can define a background generalized metric that I'll call GF from omega F, right? With no beta twisting, right? Beta is just our way of pulling back these generalized Hermitian metrics to our background holomorphic Courant algebroid. So like that's where these beta terms come from. Yeah. Because of our condition on cohomology here, there has to be a beta naught in wedge 2,0 such that del bar beta naught is del omega f. Oh, looks like a subscript. Del omega f minus del omega 0. And then we can define G naught using this data. Okay. So like if there were no beta here, it would be it'd be a generalized metric on the I del omega naught holomorphic Courant algebroid. You pull back by this beta transform, and then you get one on QF. Streets and Tien have already shown short time existence, so we don't have to worry about that. So we've got short time.
Can I ask a question about this beta?
Yeah.
So I guess I was wondering before, why does the pluriclosed flow preserve the holomorphic Courant algebroid? And is the point is that that's because when you're putting in the beta, it allows you to stay on the same holomorphic Courant algebroid?
Yes. Yeah. I believe so. I believe the way beta is defined makes it so that you like can pull back to the same holomorphic Courant algebroid. Is that right, Mario?
Yeah, so maybe one comment. So with the integrability condition that you wrote, b bar beta 0 equals del omega f minus del omega 0, the current algebra, the background current algebroid, and the one defined by omega naught may be different. But the holomorphic vector bundles are isomorphic, and actually the isomorphism is beta. So to do this thing,
So what's
you
different
don't.
about them?
Oh, the structure of holomorphic current algebroid may be different by twisting by a 3-0 form the bracket, but the holomorphic vector bundle underlying is the same. And in any case, it is true that the pluriclose flow preserves the holomorphic current algebroid. But to compare it to the background, you just need the two holomorphic vector bundles to be isomorphic. You don't need the actual holomorphic current algebroid to be isomorphic. Just the underlying holomorphic vector. But yes, the pluriclose flow preserves the holomorphic current algebroid of omega naught.
But if you didn't have the beta, then it wouldn't be true. Is that right?
Yes, what I'm saying is that just by definition of pluriclose flow, the holomorphic current algebroid defined by omega naught, by del of omega naught, is preserved under the flow. Yeah, and this integrability condition that Josh is writing is slightly weaker because it's only taking care of the 2,1 component of the forms. So you are missing some information coming from the bracket, but this plays no role on the analysis.
I see. Thanks.
Yeah, maybe I just add like, yeah, I mean, somehow it's a bit strange. Like you don't need the beta, of course, to define pluriclose flow in principle. But it's only with this attached PDE for beta that you have this appropriate capital G Hermitian metric, which satisfies the equation Josh said. So, but maybe that's not what you were asking. Yeah, I mean, like the underlying holomorphic structure, yeah, it's fixed. It's coming from del omega naught.
I have a related question to what you just said. Can you hear me?
Yeah, please.
Yeah, so what if I just assume that rho bismuth one part is 0? Would it imply on the compact background that 2-0 part is also 0, or it might be not?
I believe that's true, but I've never actually written down a proof of that. But yes, I'm pretty sure that's true. But yeah, but that's
Sorry, what is your assumption that the 1,1 component of the full
Is it
correction?
possible that one component vanishes, so the naive definition of pluriclosed flow without any beta is actually stationary? But if you write down the equation for beta, meaning considering 2-0 part of bismuth Ricci, then that would be non-zero.
I think it's true, yeah, because you sort of have this basically using the d rho bismuth is 0 and some integration by parts. I think it follows, but I'm not completely sure. I think it's not completely obvious. I think you have to use this like some explicit form of bismuth Ricci maybe to make it work.
I also kind of wonder if it no, it's not DD star. I feel like I always mess it up. But I think it's like D, like J theta or whatever.
Yeah, that's basically right. Yeah.
Yeah, it's like in the ballpark. I feel like you could use this identity to get something in that direction.
Well, yeah, the 2-0 part is just the 2-0 part of DJ theta.
Yeah, but like yeah, I don't know. I feel like the 1,1 vanishing would say something about the 1,1.
I mean, yeah, I guess like the 2-0 part, I guess just because rho bismuth is closed, the 2-0 part is automatically holomorphic. And then the question is, can it be, I guess it's like holomorphic and del exact. But it's a good question.
Yeah. Yeah, so we're starting to get towards the 70-minute mark.
How much more did you have to discuss?
I had kind of wanted to finish out the paper, but
yeah. How much more time do you think? Was more my question.
I could just sort of like state the results and not give very detailed proofs. I could probably do it in like 10 to 20.
Sure, that sounds perfect. Yeah.
Okay. Yeah, so then like once you have the short time existence here, we really just make use of these G, T, G tilde. This guy's negative. It's let me actually save that term. It's minus epsilon squared, and we've got a bismuth flat background. So we have a Chern flat G tilde. So all our bad terms drop out. And you've got something similar for the norm epsilon squared term. Right, this is the grad epsilon squared, grad bar epsilon T star epsilon squared, which is non-positive. And you can use like fairly standard arguments. I won't bore you with them too much. These imply like a priori estimates. Lambda inverse G tilde less than G, less than lambda G tilde. And like epsilon squared controlled by lambda. And then you can just bootstrap from here. Well, I mean, really, you need like, this also implies that this quantity is non-positive, and that lets you do parabolic bootstrapping, right? So from here, or let me write down the estimate, that guys. So this is T epsilon squared controlled by the initial data over T, right? This is like your parabolic regularization for any T positive. This is like your regularization estimate. And then from here, you can do like parabolic bootstrapping. By the shatter estimates to C infinity. So you get long time existence, right? This will imply long time existence. Convergence ends up following from these C infinity estimates. And yeah, I mean, so like if, I won't give the whole argument, but just if you have a sequence of points, like sequence of times Ti going to infinity, then these GTIs have to have a subsequential limit. G infinity, just because we have uniform C infinity estimates, so like Arzella, Scully, and stuff kicks in. We get G infinity, our subsequential limit, and we have to have the GTI, call it K or something, GF needs to converge to epsilon G infinity GF because we have smooth convergence. But our regularization estimate, right, our like parabolic regularization estimate says that as time gets large, our epsilon squared is going to go to 0. So this guy should also be 0. Okay, so this is going to imply that G infinity is Chern flat. It's Chern flat, and it's going to induce like a little G infinity induces a little g infinity, which is Bismuth flat. Okay. And again, just because we're running out of time a little bit, you can get that the whole flow converges to g infinity by the a priori estimates. A priori estimates will imply that the whole flow will converge to g infinity. Okay, and that's kind of one of the main results of the paper. This result is interesting for a lot of reasons, right? It implies existence and convergence on the Hopf manifold, on the Hopf surface, for example. And because H21 is small for the Hopf surface, we can actually we know exactly what omega infinity is, which is nice. It also gives us the contractibility of the space of generalized Kähler metrics, of generalized Kähler structures. Contractibility of the moduli space of generalized Kähler structures. Right. So just a quick corollary of the result we've already proved. If M2N omega Fj is compact and Bismuth flat, right? Compact, complex, Bismuth flat. If Gij is generalized Kähler on M, right? It's a generalized Kähler structure on M such that the J Kähler form of G is cohomologous to the flat background metric, right? In H21 del do. Then the solution to it's called generalized Kähler Ricci flow, GK Ricci flow, with this initial condition. Exists for all forward times and converges to a Bismuth flat structure. Converges to a Bismuth flat structure. G infinity, I infinity, J. And we also have, so like in particular, I is biholomorphic to a complex structure which is compatible with a Bismuth flat metric. I won't give the proof, but just as like a couple quick definitions. I kind of figure everybody in here knows what a GK structure is, but just in case, right? So Gij is called a generalized Kähler structure. If DIC of the I Kähler form is minus the JC of the J Kähler form. And we've also got generalized Kähler Ricci flow. So GTIT beta t is said to be a solution. Solution to generalized Kähler Ricci flow if right, beta t is a J20 form, omega t is a real J11 form. Oh, sorry, wait. Omega t is G GT J dot and they flow by the following. D omega t dt is minus rho bismuth omega, let me call it JT of the J11 part. And beta is going to flow by the J20 part, and I, the complex structure, right? I is a complex structure, which flows by a Lie derivative term. Where these theta i's are I, D star, omega I, and similar for J. All right, so you'll notice it's just pluriclosed flow with extra structure. All right, this is like PCF. This is extra. So the way we apply the previous theorem about existence and convergence on Bismuth flat manifolds is like pretty obvious. You just slot omega j in as the initial condition. Everything kind of percolates through. And because I is evolving by Lie derivative terms, you've got diffeomorphisms you can pull back by. You get estimates on the diffeomorphisms because you've got estimates on everything else. And so the limiting diffeomorphism has to be smooth and thus a biholomorphism. And then the last thing I wanted to mention that I think I'm not going to have time for, but I at least want to state it because it's a really cool result. We're actually able to get existence and convergence on manifolds with positive or non-negative Kodaira dimension. So this is, sorry, not convergence, I think just existence. Existence on complex surfaces having non-negative Kodaira dimension. So I'm just gonna state this one, and then I'll call it quits. So if M4NJ is a non-Kähler surface, non-Kähler complex surface, complex surface, I think I should compact complex surface of non-negative Kodaira dimension. Then if we're given omega naught pluriclosed, right, a pluriclosed metric, the solution to pluriclosed flow exists for all forward time. I believe there should be something about like minimality in here. I think I might be stating this a little too loosely, but like this is the main point. We can get long time existence on these compact complex surfaces having non-negative codiron dimension. And this really just comes out of the Schwartz lemma. And we were also able to prove that every cohomology class of a pluriclosed metric on these admits a metric invariant under like a T2 action. And these are all finitely covered by total spaces of principal T2 bundles. And then you apply Schwartz lemma, you get some a priori estimates, and everything else falls out nicely for us. Yeah, so I guess this is the point where I stop and ask if there's any questions.
Yeah, thanks, Josh.
Yeah, no problem.
Yeah, what other are there other questions?
Can I ask a question
Yeah, please.
about the main theorem? Not this main theorem, but the other one.
Yes. This one.
I was just wondering, because I think that you could state the hypotheses and the result does not involve exact current algebroids. So I was wondering, what about the proof actually? Like, what does the current algebroid give you?
So the Courant algebroid actually shows up here. This is like a sneaky way of saying that the holomorphic Courant algebroids are isomorphic as holomorphic vector bundles. And then using that, we're able to rewrite pluriclosed flow as this like Hermitian-Yang-Mills equation for Hermitian metrics on the holomorphic Courant algebroid. Yeah. So I mean, like that's where this cohomology condition comes from.
I think strictly speaking, I mean, that's really just a structure of the holomorphic vector bundle, I guess. Maybe that's what you're getting at.
Oh, okay.
I think it's still maybe not totally clear. I think maybe Mara had some idea it had something to do with the convergence of the flow, but maybe not. I guess or go ahead.
No. I think the full structure of holomorphic algebra doesn't play a role. It's just the underlying orthogonal holomorphic vector bundle. So, but as you saw as I explained in my previous lecture, actually the way you naturally obtain this generalized Hermitian matrix is via reduction. So everything fits very nicely in the setup of generalized geometry. But for these analytical results, you don't need the full structure, just the underlying holomorphic orthogonal vector bundle.
Yeah, I mean, yeah, you wouldn't really have guessed any of this without generalized geometry, but in the end, yeah, the Courant bracket. Well, I mean, you can sort of motivate the twisted D-bar structure sort of using the Courant bracket as well, right? But strictly speaking, it can all be sort of boiled down to just this certain holomorphic vector bundle and some Hermitian metrics on it. Yeah, that's true.
So the holomorphic bundle is kind of crucial. You couldn't like boil that down to just the little g and the beta on the surface.
Well, no, yeah, see, you could also do that. Yeah, like in principle, these are all just maximum principles involving like g, beta, and del omega naught. But I think they would look blindingly strange. Like I played around with those for literally like years and could not see these things. But somehow it's totally trivial with this generalized point of view. So
interesting.
Yeah, it's like I mean, so like this, right here. Yeah, I mean, like it seems really strange to take this combination of G and beta, or even to like have a flowing beta. But it is like Jeff said, I mean, when you take like the generalized geometric perspective, it becomes pretty clear why that should happen. And then you get just like such a nice evolution equation from it.
Yeah, nice.
Thanks.
I actually, just a comment, I actually find it exciting that the generalized geometry appears in the proofs, but not in the statement
Right.
of the results.
Yeah, that's true. That's true.
It always feels like, I mean, like I know it's not that, but it feels like a Fourier transform kind of thing, where like you Fourier transform the problem and then you get an easier one to work with. I don't know. I just think it's funny that you've got this identification between this guy and
I mean, it's a very useful language. You sort of dissolve it in this language, and all these difficult tensor identities become trivial, sort of.
Yeah.
Quite nice. Yeah.
Yep.
But okay, if there's nothing else, yeah, okay, let's thank Josh again.